For week 3 material, we're going to be talking about arrays. So an array is just a collection of data values that's organized in rows and columns and has a single name. So you might think of it as a matrix. You can see here it has m rows and n columns. And it turns out the fundamental unit of data in MATLAB is the array. So there's different kinds of arrays based on their size. We've been dealing with scalars, which is just a 1 by 1. We always talk about the dimensions in terms of rows times columns. So a 1 by 1, 1 row, 1 column. A row vector has 1 row and as many columns as possible, or as many columns as necessary. A column vector has as many rows with 1 column, and then a matrix has more than 1 row and more than 1 column. So in order to create an array, we are going to use brackets. These are square brackets. We will use them quite a bit. We're going to talk about the different kinds of arrays. We already know how to create scalars, so we'll talk about row vectors, how to create column vectors, and how to create matrices. So to create a row vector, there's 3 different methods. The first one is just by typing in the elements. And when we type in the elements for a row vector, we are going to separate them by spaces or commas. So here you can see spaces or commas, and it turns out spaces and commas put things next to each other. So you can see over here in MATLAB, I have some examples started. So if I go ahead, here I've created a row vector, and I put them next to each other with commas. You'll see me use both. You'll probably see me use spaces in class because they're faster to type. And we can see how it's printed out. And over in the workspace, we can see that it's a R1, the different values it contains, and it's a row vector with a size of 1 by 7. The second way to create a row vector is using the colon operator. So the colon operator allows us to create a linearly or evenly spaced vector given 3 numbers: the starting value, the spacing, and the ending value. And here's what it looks like to do the colon operator. We start with our starting value. So let's say we want to start with a value of -2, followed by a colon. Then we have our increment. So say we want to increment by 0.5, and then we have our ending value. Let's say we want to go all the way to 2. So it's going to start at -2, then add our spacing. So -1.5, then add our spacing to -1, and then keep going all the way until we get as close as possible to 2. So we can see over here in MATLAB what that vector actually looks like. So it goes -2, -1.5, -1, etc., all the way up to 2. And in our workspace, we can see it's 1 row and 9 columns. So it's a row vector. The third way to create a row vector is using what's called the linspace function. So it's a function, so that means we type the name of the function followed by open close parentheses. And the linspace function has 3 input arguments. If we type help linspace down here, it will tell us a little bit how to use it. But there's 3 input arguments. So it generates endpoints between x1 and x2. So we need to know what value we're starting with, what value we're ending with, and how many points we want in between. So we can see that's demonstrated over here in my notes as well. So if I look at the linspace function here, I'm going to start at -2, end at 2, and have 9 values. Oops, I forgot the semicolon. So here you can see that's what that vector looks like. And it turns out it's the same vector I created with my colon operator, but here's a second way to create it. So there are 3 ways to create row vectors. Column vectors. There are 2 ways to create column vectors. The first one, just like with row vectors, we can start by typing in the elements individually. But rather than separating them by commas or spaces, we want to separate them by semicolons. So semicolons stack things on top of each other. So here you can see separated by semicolons. Here we can see an example of that. In our workspace, or in our command window, it shows up with the values actually stacked on top of each other. In our workspace, we can see it's a 7 by 1, so 7 rows, 1 column as a column vector. The second way to create column vectors is using the transpose operator, the transpose function. We don't typically use the transpose function because the operator is significantly less things to type. It is the apostrophe. It's very subtle, but very powerful. It converts rows to columns and columns to rows. So here, to create this vector, I'm going to go ahead and take the values in R1, which R1 look like this, and I'm going to transpose them. So when I transpose them, it took my row and it made it into a column. Same values, just now it's a column. I can do this with any valid method to create row vectors, so I can use the linspace function. So here I'm going to use the linspace function, create a vector between -2 and +2 with 21 values, and now I'm going to transpose it. So we can see what that one looks like. Or I can use my colon operator between -2, a spacing of 0.2, go all the way to 2, and transpose it to create that vector as well. Same vector, 2 different methods. So 2 ways to create column vectors. A matrix. A matrix is essentially created by typing in rows separated by semicolons. So semicolons with rows to stack them on top of each other, or columns as commas to put them next to each other. So semicolons stack things on top of each other, commas separate things, put things next to each other. So here I have 2 examples shown. So here I have rows with a semicolon. Here I have columns. Nope, that's the wrong one. Here I have columns with the comma. We typically do rows. And we can see examples of this. So here I have 1 row, 2 rows, 3 rows, separated by semicolons. Note, spaces put things next to each other. So here's what that looks like in MATLAB when it's created. In my workspace, I can see it's a 3x6. It has 3 rows and 6 columns. Here you can see I have columns separated by commas. In order to do this, they have to be individual or column arrays. Here they do not have to be in brackets for each row. Either way is valid. We typically do this method here. So here we can see what that one looks like. Same idea, I just put each individual column separated by commas. I can also do it in one line. You can see it here. So here what I've done is I've put a row, comma, or semicolon, row, etc. And I've transposed it. So that's another thing. It takes these rows and makes them columns. I can also create rows using the colon operator. Your rows can be created with any method, essentially, any row vector method. So here, this row goes from 2 to -8 with a spacing of -2. This one has goes from 4 to 24 with a spacing of 4, etc. You can see what this one looks like. There's that first row from 2 to -8. Here's that second row from 4 to 24. The key thing is all of our rows have to have the same number of values. All of our columns have to have the same number of values. Here's another example where I create my rows with the linspace function. The last example we can see is through this method here, where each of our rows are separated into individual lines of code. So row 1, row 2, and row 3 are individually created. And then when I create my matrix, I'm going to put row 1 on top of row 2 on top of row 3. So note, semicolons stack things on top of each other. Spaces or commas put things next to each other. All 3 of these methods are valid ways to create this matrix of values. Which brings me to concatenation, which essentially is what we just did. Concatenation is by combining matrices or vectors in order to create a new matrix or vector. So this is where it's important to understand commas put things next to each other, semicolons stack things on top of each other. And we just saw we did this with rows. Here we did it with rows. We can do it with columns, putting them next to each other with spaces or commas. And it turns out we can also do these with matrices as well. And we will do examples in class. There are a bunch of functions that are really useful in order to determine information about an array or create predefined arrays. The size function returns the number of rows and or columns of the array. The length function returns the number of elements in the largest dimension. Numal returns the number of elements in the array. Ndims returns the number of dimensions. So is it a scalar? Is it a vector? Is it a matrix? And then these ones create arrays with defined values. So if we want to create an array that's all full of zeros, we use the zeros function. If we want to create an array with all ones, we use the ones function. If we want to create a identity matrix, so this is the identity matrix, it looks like this. That's the identity matrix for a 3x3. You can see it's zeros except for ones along the diagonal. We can use the I function. And if we want to create a matrix with random numbers, we can use the rand_i function, and you'll see me use that quite a bit in class. So those are all the methods that we can use in order to create arrays. And we can see what they look like in our command window. We can see what they look like in our workspace, identifying the size. If you don't have the size in your workspace, you can right-click on this bar up here and add more information. Click on size and it will show you. If our array is too big, it will not show the values, but if it's a small number of values, you'll see a preview of what those values are in the workspace. So that's creating arrays. Next, we want to talk about indexing. So indexing is the art of modifying the values in our array or accessing. Either one is valid, but indexing is what we use in order to access and modify individual elements. So if I have an array, let's say I have an array that, 2 rows, 3 columns. All of these values here have a specific location. These locations are identified by what's called their index. So index locations start at 1, and they increment as integers, ending with the number of elements. So for this row here, it's indexed 1, 2, 3. For this row here, it's also indexed 1, 2, 3. You can index more than one location at a time, and it depends on whether or not you're talking about a vector or a matrix with how the indexing occurs. So first thing, indexing vectors. Vectors are one dimension. So if I have a vector with 5 elements, they're indexed with 1, 2, 3, 4, 5. So these are their index locations. They could also be their values, but they're index locations. If I want to index a single number, I just indicate a single number. So if I want location 2, I say the name of my vector followed by open close parentheses, and then what number I want to index, which location I want to index. So here's another instance of how we use parentheses. We use parentheses in order to group together calculations. We use parentheses to give data to a function, do our function inputs, and now we use parentheses to index an array. And we can have more than one location we want to index. So if it's not a single location, let's say I want location 2, 3, and 6, if it exists. So I just put in an array of locations. Same thing for a row vector and a column vector. So here we have some examples. So let's say I have a vector v. It's a column vector. It looks like this. It doesn't matter if it's a row vector. The same thing would happen because it's all one dimension. 1 corresponds to the first location. It doesn't matter if it's in the row or the column. 2 corresponds to the second location, etc. If I say v1, it's going to grab the first location in v, which happens to be a 1. So v1, the first location, is a 1 value. If I say v1, 2, or 1, 2, it's going to grab the first 2 values, so 1 and 2. If I say v2, 4, 5, it's going to grab the second number, the third, fourth number, and the fifth number, which corresponds to this 2, this 13, and this 2. Here, I have fancy notation, so I didn't mention this, but this is shorthand for an increment of 1. So this is another way to type an increment of 1. I don't need that 1 there. It does the same thing. So here I'm indexing locations 3, 4, and 5. So here's locations 3, 4, and 5. It corresponds to the 11, 13, and 2. Here I'm indexing locations 1, 3, 5, and then I get as close to 6 as but not possible. So 1, 3, and 5. So these I'm indexing the odd numbers. Here I'm indexing 2 to the length of v. Length of v is one of those functions that we talked about. Length returns the number of elements in the largest dimension of an array. So for a vector, it's the number of elements it has. So starting at 2, incrementing by 2, all the way to the number of elements. So 1, 2, 3, 4, 5, 6. So it's going to index all the even numbers. So 2, 4, 6. So element 2, 4, 6. And in indexing, there's this fancy word called end. End automatically indicates the last element in the dimension. So 2, 2, 2, end will indicate the last location automatically in this vector, which corresponds to the 6. So here it's grabbing 2, 4, 6. So the 2, the 13, and the 23 again. So that is how we index a vector. We just need one set of numbers or one array of locations to access, and that array can be created any valid way. Here I've typed in numbers explicitly. Here I've used the colon operator with various functions. Second, indexing matrices. So matrices have 2 dimensions, which means we need to indicate the rows that we want to index and the columns that we want to index. So here's my matrix, open close parentheses. I indicate the number of rows that I want, followed by a comma, the number of columns, or the columns that I want to index. It can be an array of rows and an array of columns as well. So here we can see a matrix that I've created. So it looks like this down here in my workspace. And if I want to grab the second row, 4th element, oops. Made a little error there. So here's what my matrix looks like. If I want to index the second row, 4th column, so row 2, column 4, it's going to give me 14. Here, I'm indicating I want to grab the 3rd row, columns 1, 4, and 6. So in the 3rd row, I'm going to grab this number, the 15, and the 23. So it puts those in a vector there. Same orientation, it just grabs the numbers. Here, I'm going to grab rows 2 and 3. So here is once again my shorthand notation for an index of 1. And column 5. So rows 2 and 3, column 5. So this 18 and 19. So it grabs those numbers. Same idea here. Rows 3 and 4, columns 1, 2, and 5. So now I'm grabbing bigger subsets. It's always going to be a rectangular set of values when we're talking about indexing matrices. So here I'm indexing from row 2 all the way to the end, so the last row, so 2 to 4. And then here I'm grabbing columns 1, every other one, so 1, 3, 5, and then I'll stop when I get to the end. So here's that set of values that I've grabbed. So rows 2 through 4, and then columns 1, 3, and 5. There's also this fancy notation where I have a colon. When you see the colon, that indicates that it's all of the rows or all of the columns. So I want all of the rows in column 3. So that grabs column 3, which we can see corresponds to this one here. Or here, I want to grab row 2, all of the columns. So all of the columns in row 2. So that's all of row 2 we can see here. So we've got some fancy indexing notation. We've got the end keyword, where for this matrix, end for rows indicates 4, end for columns indicates 6. For this vector, end indicated 6. And then lastly, we can see I want all of the rows in columns 1, 2, and 3. So here it grabbed those. So for a matrix, we can use 2 sets of numbers. We can identify the array of rows we want to access, comma, the array of columns we want to access. There's also something called linear indexing, where we index based on a single location. So for a matrix, the linear indexing is 1, 2, 3, 4, 5, 6, 7, 8, 9. So each individual value has a single number associated with it, starting with the value in the upper left is 1, going down the column and then working over. So we can also index a matrix with a single number. Less often it happens, but it is possible to do that. We already talked about the end keyword. We already talked about colon operator. Here's a table that indicates that colon operator. So if we have with just a single colon, that's all of the elements. It will place them into a column. If I have a single colon for the rows, that means it's a single, or all of the elements in that row. Or I can say all the elements in the row with an array of columns, or vice versa. I can say for a single row, all of the columns, or for an array of rows, all of the columns. So there's my colon notation for indexing. Do not confuse this colon notation with creating an array. It is separate. So the colon operator is used in different ways. It can be used to create a row vector, like we talked about up here, or it can be used in indexing to indicate all of the rows or all of the columns in the array. The last thing to talk about or to introduce is modifying an array, so changing the values in an array. Each individual element in an array can be individually accessed and or modified. Each submatrix in this array can be modified, can be accessed. Each row can individually be accessed. Each column individually can be accessed. And it really comes down to two different sides of the assignment operator. So variable equals value. Variable equals expression. That's what we've been doing previously. But now we're going to expand on that, and it's going to be more along the lines of where to store something, equals what to store there. That's what it's going to come down to. Where do we want to store it? And what do we want to store there? Previously, we wanted to store a single number inside of a variable. But now we can store a single number in part of an array, or a array inside of another array. So we're going to indicate which variable we're modifying. Where in there, what locations to modify. And over here goes what are we going to replace it with. So now there's more questions to ask. Note what locations we want to modify needs to match what we're going to put there, and we'll see what that looks like. So over here, looking at examples. So let's say I have M. M is going to be filled with ones. It's going to have 7 rows, 10 columns. Here we go. M's pretty large. I'm going to go ahead and start changing values in M. First, I'm going to change inside of M. I'm going to change the second row, 5th column, and I'm going to store a 100 there. So now in the second row, 5th column, M now has a 100. Then I'm going to go ahead and change a bunch of things to 0. So in rows 1, 3, 5, 7, so this indicates 7 because that's the number of rows. This end indicates, how big is M? 10. So this part indicates 10 because that's the number of columns I have. So it's going to modify columns 1, 3, 5, 7, and 9, and it's going to assign all of those locations to 0. So we can see every other row and every other column had a 0 placed there. So this single number is placed in all of those locations. Here, I'm going to modify rows 2, 3, 4, and 5, columns 4 to the end, so 4 to 10. So that's this array here. And I'm going to put these values, a random set of numbers, 4 rows, 7 columns. So that's how we use random. So note the number of values on this side matches the number of values on this side. So this array is essentially placed over these locations inside of this array. So we can see now M is changed. Rows 2, where is it? Rows 2 through 5. So 2, 3, 4, 5. And columns 4, 5, 6, and 7. So here, this subarray was modified, was changed. Keep in mind, the number of elements on this side matched the number of locations on this side. If I had changed this to 2 rows, 7 columns, and we redid this, there would be an error that is formed. It would say unable to perform assignment because over here, I have a 4x7 of locations, and over here I have a 2x7. So it needs to match on both sides. If we want to delete elements, we can assign it to an empty bracket, empty array. So here I'm modifying the first row and the last row in all columns, and I'm deleting them. Now they're gone. The first row and the last row are gone. So rather than it being 7 rows, there are now 5 rows. Same thing here. I'm going to delete all the rows in columns 1 to the end. So now I've chopped off the first row and the last row. Whenever you delete elements, though, it needs to be an entire row or rows or entire columns at a time when it comes to a matrix. The last thing to mention is that new locations can be created by just assigning values to desired locations. So here, this M matrix is a 5x8. It has 5 rows, 8 columns. Let's say I want the 7th row, 9th column, to be a 1. That's totally fine. What happens is MATLAB is going to go ahead and create extra rows that it needs. So it needs 2 extra rows. It's going to create the extra column it needs, fill it with zeros, and then go ahead and put a 1 in the location that I specified. It's a weird thing that it can do, but that is what it does. And there we go. That is all the data that all the information for week 3. My examples did go through a little bit deeper than what I talked about in the notes. But key things to note is, key things to note, commas and spaces. Commas are put things next to each other. Semicolons stack things on top of each other. That is crucial to understand. Other key things to note. This whole idea of how we index things. Where to store something equals what to store there. Asking ourselves, what variable are we modifying? What locations do we want to modify? What do we want to put there? Making sure those numbers match. So those are key things, and we will go over lots of examples. We will go more in depth on the colon operator. We will go more in depth on the linspace function, and we will explore all of these examples and